out the order of the reaction, then we can do something really useful with it. And we're going to see what we can do today. Make sure you have a coin available for partway through our lecture. The assignment that was due or is due, it's Wednesday? It's Wednesday today, yeah. The one that was due tonight, we're extending it just to give all the sections a chance to review that material. Okay, so last class, we analyzed this experimental data. Some scientists did 3 experiments, changing the initial concentrations of hydrogen and nitric oxide. And they were careful, good scientists, measuring their concentrations and measuring how the reaction rate changed from run to run with those changing initial concentrations. And we could see, for example, that if the hydrogen concentration doubled at the beginning, we started with a higher concentration, well, the rate followed suit. The change in initial concentration of hydrogen matched the change in rate. Both were multiplied by 2. That must mean, in the rate law, the concentration of hydrogen is to the power 1. And we could predict that it's a first order according to hydrogen. But if the numbers get more complicated, or we want to confirm that our prediction is correct, we can compare the rate law for run 2, divide that by the rate law for run 1, and calculate and solve for what that exponent x is. And of course, it was 1. And if we did the same thing to solve for what y would be, the exponent for nitric oxide, we can solve rate law for run 2 over, or actually I think we did rate law 3 over rate law 1, and we can solve for that exponent. So the rate law is first order according to hydrogen and second order according to nitric oxide. And overall, we can add up those exponents. Overall, the rate law would be 3. Overall, the rate order would be 3. But we're not quite done. This problem asks us to solve for the rate law. We've solved for both of these exponents, but we still need to solve for k. So we're going to jump to a new slide and solve for k. We now know what these exponents are. We can choose any run. For simplicity, I'm just going to choose run number 1. Plug the data in for run number 1. We can use the rate from run 1, the concentration of both reactants from run 1, and solve for the specific rate constant k. So we can go ahead, plug in the data that we know, and solve for k. Now, when we're solving for specific rate constant, we do have to keep track of our units because it matters. So I've carefully plugged my data into this rate law. I want to isolate for k, so I'm going to rearrange and show you how I solve for k while I keep track of my units. So I divided both sides by 0.1 times 0.2 squared. 0.2 squared gives me 0.04. But I also need to square the units, and this is where it can get a little bit loopy. We want to solve for k, and on our calculator, it's nice and easy to divide 5 divided by brackets 0.1 times 0.04. That gives us 1250. But then we need to sort out the units. I have moles per liter and moles per liter in the numerator and denominator. Those factor out. I'm left with per second in the numerator. And then I have molarity squared in the denominator. So I can rewrite that on the same line without having to use a fraction by turning that exponent to the -2. As a reminder, if we had something like per second or second to the power -1, that's equivalent in fraction form as 1 over second. Now, moles per liter is molarity. So we could also write it as, in a fraction form, second in the denominator, and then molarity squared in the denominator, or just so you can see another way, it is moles per liter, and it's squared. So that's another way of writing and interpreting the units for this specific rate constant. So what's the rate law? Well, the rate equals the specific rate constant with units hydrogen to the power 1 and nitric oxide squared. Based on these values, we could predict the rate of this reaction, and this would be the overall rate law. So when we're analyzing experimental data, often, sometimes, we can just figure out the order of the reaction by inspection. It doubles, the rate doubles, well, that must be first order. It doubles, the concentration doubles, the rate doesn't change, well, it must be 0 order. But then sometimes we get numbers that aren't quite as easy to solve off the back of our hand. Or we don't have 2 runs where only one thing changes. Multiple things are changing. So we actually do have to divide those 2 rate laws to be able to confidently solve for those orders of the reaction. So let's do one more example where we want to determine the rate law. For this experiment, it's reactant A turning into products. A is some generic reactant. We don't really know what it is. But the first run, the concentration is, as you can see here, and the rate was measured. For the second run, the concentration was changed. Now, off the top of my head, that doesn't look like it doubled, nice and simple, like in the previous problem. And the rate changed, but again, off the top of my head, it doesn't look like a double or a quadruple or something really simple. So I'm going to solve for the whole rate law, and I want to start by solving for that exponent. What is the order of the reaction according to A? I'm going to go ahead and calculate it rather than just doing it in my head. I want to compare the rate law for run 2 divided by run 1. So I'm going to use the data from the experiments, from each run. I have one equation and only one unknown, so I can confidently solve this. On the left-hand side, the rate for run 2 over the rate for run 1 gives me 1.265 as the number. The specific rate constant, at this point, I don't know what it is, but as long as the temperature was constant, it's constant as well, and it factors out. Both of these concentrations are to the power x, so I can divide these concentrations, gives me 1.601, which will also be to the power x. I need to isolate for x. I need to bring that down from its exponent location. So I'm going to take the log of both sides, which allows me to bring this x down. I can isolate for log by dividing both sides by log 1.601. I'm just showing an intermediate step here. X is 0.5. Kind of weird, but it can certainly happen. We can have a rate order that's 0.5. And this is why sometimes the 0.5s are a little bit more difficult to identify. So we've identified the order of the reaction according to A. It's a half order reaction, but we still need to solve for K to have the overall rate law. I can choose any run, put that data into the rate law. The only thing I won't know, now that I know that exponent, is k, and I can solve for k. So let's go ahead and do that. I'm going to choose run 1 just for simplicity. You're welcome to use run 2 if you want. Now I have exponents in a fraction. Mole is to the power 1 in the numerator and to the power 0.5 in the denominator. Exponents I can simply subtract when they're in a quotient being divided like this. So 1 minus 0.5 gives me mole to the power 0.5. And per second isn't factoring out with anything else. And liter, we have -1 on the top, subtract -0.5, which is like adding 0.5, which gives me liter to the power 0.5. So now we know our specific rate constant k. We could put this back into the rate law and solve interesting problems and predict the rate of a reaction given initial starting conditions of A. These exponents, the order of the reaction needs to be determined experimentally. It's not like a specific rate constant k where we can just look at the reaction, the overall reaction, and figure out what they are. We have to analyze the experimental data. But once we have done that, then we can reach to our integrated rate laws. We can delve into some really rich formulas that allow us to analyze reaction rates. First, we have to know if the reaction order is 0 or 1 or 2. That's going to be what we're talking about in our course. Once we know if it's 0 or 1 or 2, we can pull on that set of equations and solve some really interesting problems. We've been looking at rate laws. Rate equals specific rate constant k times the concentration to whatever order the reaction is according to that reactant. But now we're going to integrate these rate laws. We're going to get a richer set of formulas to be able to pull from and analyze reaction rates. If we're going to start with first order reactions, and that's probably going to take us to the end of the class. We'll see if we get onto 0 in a second today. If the reaction is first order, we have seen this rate law before. It's going to be the concentration of A to the power 1. We don't usually write in ones, but I will just so we remember it's a first order reaction. Well, this is also equal to the change in concentration of A over the change in time, or negative delta A over time, because rate is a positive value. Now I can rearrange this equation where rate equals, I'm just going to take this concentration of A and bring it to the denominator, take my delta T and bring it up to the other side, move my negative sign, and I can get negative K and delta T, or change in time, is equal to 1 over the concentration of A and the delta A. Well, I can go ahead and integrate over time, the concentration of A at the beginning and the concentration of A at some specified time. This is just for fun. You don't actually have to integrate it. The integrated formula is provided to you, but now you know where it comes from. Well, if we integrate the right-hand side, we're going to get ln A. We're going to get, well, on the left-hand side, negative KT equals ln the concentration of A at time t minus the ln of the initial concentration of A. Well, if we have the difference of two ln values, that's the same as being able to take the quotient divided by. So this integrated rate law can also be written out as you see here. Concentration of A at time t divided by that starting concentration is equal to the negative of the specific rate constant multiplied by the time. Well, if we wanted to take E to both sides, we could rearrange to this formula on the right. These are exactly the same, they're just rearranged differently. What we have here is the integrated rate law. This allows us to monitor and track and plot the concentration of A according to time as the reaction proceeds, as we use up A and produce our products. Well, look at this equation here that I'm putting a box around. This is also the integrated rate law. I'm going to take the negative ln A naught at the beginning and add it to the other side of the equation. And then I'm going to change slides. Well, actually, no, this is the starting one anyway. We're good. There it is. There's our integrated rate law, one of the ways to write that down. I'm going to move this component and add it to the other side of the equation such that I'm left with another way of writing the integrated rate law. Then I'm going to write y equals mx plus b. Now, hopefully, y equals mx plus b brings back lots of happy memories from math class where you learned about the equation for a straight line. When I do it this way, I can see that the ln of the starting concentration of my reactant is equal to y, or it's comparable to y if I compare it to a straight line equation. I could go ahead and plot some experimental data with my y-axis being the ln of the concentration of A at any given time during the experiment. Time, then, is my x-axis. So I'm starting with the concentration of A here, and it goes down as the reaction proceeds. But you'll see on the left here, the y-axis is actually the ln of A going down linearly as time proceeds because this is a first-order reaction. What if it wasn't plotted as the ln? What if we just wanted to see the concentration of A go down with time for a first-order rate law? Well, then it would look like this. Curves are harder mathematically to deal with than straight lines. So we could have plotted concentration of A going down as the reaction proceeds, but if we take the ln of A, then we get a nice straight line, which is just easier to interpret, easier to work with. If we have a straight line, then we're going to have a slope. And because we plotted ln A versus time, the slope is equal to negative k, just because it aligns really nicely. So we could plot our experimental data, and immediately, simply by calculating or reading off the slope of the line, we would know what the specific rate constant k is for this experiment. It's a really rich way and a valuable way to analyze reaction rate data. We now know the specific rate constant k. We could do a small part of the experiment and then extrapolate a little bit one way or the other and predict with pretty good accuracy what the concentration of A will be at any given time. Now, it is a first-order rate law, so there's one more way to visualize this. We could look at the reaction rate and compare that or plot that according to the initial concentration of A. We analyzed some experiments, and let's say the initial concentration of A is whatever I did this dot in, and we measured the rate. And then we doubled A, and the rate doubled. We tripled A, and the rate tripled. We quadrupled A, and the rate tripled. And this is how we figured out that it was a first order reaction. So we can identify a first order rate law or a first order reaction by changing the concentration of A and seeing that proportionally it increases the rate of the experiment. Or we can see that we get this nice lawn type curve as A goes down. Or most diagnostically, if we plot ln of the concentration of A over time and it gives a straight line, immediately we can know that it's a first order rate law. That's in contrast to a zero order or a second order. They're going to have a different set of parameters and a different set of equations to pull on. But because we integrated this, we can now calculate and predict important stuff as time goes on. So let's apply this. Let's solve some problems here. We have a reactant B turning into products. And the scientists collected this data, monitored the concentration of B over time, and then they plot the concentration of ln B according to time, and it gave a straight line. Based on just that information, that ln B versus time gave a straight line, well, it must be a first order reaction. Just based on that data, we know it behaves according to first order kinetics. And the slope of the line was run in Excel or whatever other program, and it was determined that the slope was negative 0.35 per minute. That was the slope of the line. Well, let's look at part A. If the starting concentration of B, that initial concentration, was 0.16, so I'm just going to go ahead and plot that. Right here would be ln of 0.16. We want to find the concentration of B at 4 minutes. Now, I don't know where 4 minutes is. I'm just going to guess that it's right here. I want to figure out what B is. How much B do I have left after 4 minutes of this reaction proceeding? Well, we know the starting concentration. Well, actually, we want to find the concentration of B at 4 minutes. We know the starting concentration of B. It's ln 1.6. So the starting concentration was 0.16. We can take the ln of that. We want to solve for this at 4 minutes. But what is that specific rate constant K? The problem didn't directly tell me what that specific rate constant is, but because I know how to compare this integrated first order equation to the equation of a straight line, I can line up these equations and see that the slope is equal to negative K. So because it gave me the slope, I know that equals negative K, and lo and behold, in my equation, I need to put in negative K. So I can interpret that and plug in the K value. I can solve for K and then take the negative of the K, and that gives me the slope. So we can plug in what we know and solve for the concentration of B at 4 minutes. Now we've solved for ln B, but I don't want the ln B, I just want B. So I can take the e, the exponent of both sides, to isolate simply for B. Therefore, after the reaction proceeds, the concentration will have gone from 0.16, click, 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 all the way down to 0.04, which is what we would expect, that concentration going down. So that's part A. We have this nice integrated rate law, we can do something useful with it. But it's also important to know how to choose which equations to use. So just by a show of hands, for part B of this problem, find the time required for B to drop to 0.1 moles per liter. Which equation should we use to solve this problem? I'll give you 10, 15 seconds to chat with the person beside you. And 3, 2, and 1. Who says A, we should use the top equation? Who says B? Who says C? And that is correct. Definitely the integrated first order rate law. I didn't trip many people up. That's a first order rate law, but it's not an integrated one. It doesn't have time as part of this equation. So we want to use B. So we want to find the time required for the concentration of B to drop to 0.1 moles per liter. So now we know what the concentration of B is at a particular time. We want to solve for time. We know the starting concentration, and we know that the slope is equal to negative K, and the slope here is negative 0.35. So it's a nice direct equation. We can solve for our unknown value. Therefore, to get us down to a concentration of 0.1 moles per liter, this reaction needs to proceed for 1.34 minutes. How did I know the units here for the time? Well, I chose them from the specific rate constant K. Maybe it's per second, maybe it's per minute, maybe it's per day. For this equation, the specific rate constant was given in per minute. Therefore, my time unit is minutes. So we can do all sorts of things, interesting things. Time analysis, once we know the order of the reaction and we've selected the integrated rate law that goes with it. Well, let's move to part C. We want to figure out the time required for half of B to decompose. Well, what's half of B? I need to pay attention to what I started with. That's my starting concentration of B. So half of that starting concentration would give me 0.08 moles per liter. We want to solve for time, given the concentration that we know would be half compared to the starting concentration. And again, we interpreted the slope to equal negative K. So we can solve for time. Now what we've just solved for here has a specific name. The time that we just solved for half of that starting concentration to react, to decompose, to produce something else, this is the half-life for this reaction. For first order kinetics, the half-life is a really important value. There are a variety of reactions that occur according to zero order and first order and second order, but all radioactive isotopic decay occurs according to first order kinetics. For if you are communicating how long something remains radioactive, well, you communicate that in the half-life. How many years until half this sample decomposes? So So we could solve for the half-life this way. We could figure out K, figure out our starting concentration, exactly half of that, use the integrated first order rate law, or we could use some of these little side direct equations. It's a nice simple way to explore the concept of half-life. So if you have a coin with you today, pull out your coin, and I'm going to ask everyone to stand up. So where you are, go ahead and stand up. Keep that blood pumping. Stand up. You have 10 seconds. It'll be more fun if you stand up. Come on. If you don't have a coin, you can pretend you have a coin. Okay, so I want your attention. 3, 2, 1. Okay, if you have a coin, there's a heads and a tails. The head is where you see the head of the person. The tails is whatever other picture you have if it's a Canadian coin. When I say heads or tails, whichever one I call out, you're going to flip your coin. If that's what you got, you're going to sit down. If you don't have a coin, I want you to choose in your head randomly heads or tails. And then if I say what you were saying in your head, then you sit down. We have a big class, a few hundred people. This is kind of like a whole bunch of atoms. And if we undergo first order kinetics or isotopic decay happens according to first order kinetics, after the half-life has elapsed, half the sample is going to have reacted. Odds are 50-50 that half of you get heads, half of you get tails, okay? We're going to do a half-life of 5 seconds. In 5 seconds, I'm going to call out heads or tails. If I call out what you have, you sit down. Ready? 5, 4, 3, 2, 1. Tails. If you have tails, sit down. 5, 4, 3, 2, 1. Tails, you sit down. 5, 4, 3, 2, 1. Heads, you sit down. 5, 4, 3, 2, 1. Tails, you sit down. 5, 4, 3, 2, 1. Tails, you sit down. 5, 4, 3, 2, 1. Heads, you sit down. And we're going to pause. We still have a couple people. And this is what actually happens with isotopic decay. We still have a small amount of the sample that remains. Everyone can go ahead and grab a seat. Thank you. This is how isotopic decay occurs. Every half-life, half of the reactants decompose or react. Now, there's a way to calculate half-life that's a little bit more direct. So follow along with me and we'll see how this happens. If we want to calculate half-life, that's exactly half of the initial concentration. If we plug in half of the initial concentration as our desired concentration of A at time t, then the initial concentration of A factors out, and we're left with ln of a half. Well, ln of a fraction, we can take ln of the numerator minus ln of the denominator. That's another way of writing this. Ln 1 is 0. So we're left with negative ln 2, and this is equal to negative kt. We can rearrange this. The half-life, the time for half of those reactants to react, is ln 2 over k. So like 0.693 over the specific rate constant k. Just a nice little short, handy form. So if this is a half-life of 1 second, 1 second, 1 second, 1 second, and it halves, 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 and it continues to decompose. So my question for you, if we had a 1 gram sample and it went through 3 half-lives, according to first order kinetics, how many grams remain? Chat with the person beside you for 1 minute. And 10 more seconds. And 3, 2, and 1. Okay, most people went for E. Well done. We halved the sample. And then we halved it again. And then we halved it again. Another way we could write that is half to the power 3, or 0.5 to the power 3. This gives us 1/8. That means 7/8 have reacted. 1/8 remains. You did this intuitively. You didn't need a fancy formula to tell you how to solve that problem. So you don't actually need these fancy formulas to solve these problems either. But yeah, you have them. You just derived this equation here. Half to the power of the number of half-lives that elapsed. How many half-lives elapsed? Well, the total time divided by the length of a half-life. That's how many times you halved and halved and halved again. So you manually could calculate some of these problems, or at least get a pretty good estimate of half and half and half. Okay, it needs to be somewhere in there. We could plot this as well. Remember I mentioned if we plot the concentration of A according to time, it goes down in this lawn-type slope. It's not a straight line. We have to take the ln of A to get that straight line. But if we just plot the concentration of A, it goes down according to this nice curve here. Well, to half the concentration will take me 1 half-life. And then if I want to split this in half again, well, that means I've done 2 half-lives. And split it again, that's 3 half-lives. Split it again, 4. Split it again, 5. Split it again, 6. And it keeps kind of approaching 0, but if the sample is large enough, it doesn't really get to 0 technically. Here we would have gotten to 0 if we kept going on and on. But if we have like moles and moles of atoms, it just kind of approaches 0. So let's solve some problems. Radioactive decay, or isotopic decay, as we've mentioned already, always happens according to first order kinetics. So you know what? You don't actually need to be told that it's occurring with first order kinetics. If it's isotopic decay, you already know it's first order kinetics. Well, for your interest, uranium-238 is the most common isotope of uranium. Uranium is mined in Canada. My father-in-law was actually a uranium miner up in Elliott Lake when he was younger. Uranium can undergo natural isotopic decay. And part of the journey for uranium decay, just naturally in the rocks, goes through radon gas. It's the only gas in this process. So all of a sudden, the rocks that were like solid and buried in the ground can evolve into a gas, and that can seep into basements. And this is why you have to check radon levels in some older buildings. But each of these steps has its own specific half-life. Some of them are minutes, some of them are years, one of them is less than a second. Each of these isotopic decays has its own half-life. Well, polonium-210, right here, so there's the atomic mass, the atomic number, polonium-210, it has a half-life of 138.4 days. What fraction of polonium-210 remains after a whole year? Well, how many half-lives have elapsed? 1 year would be about 365 days. We know the half-life is 138.4 days. After a whole year, 2.637 half-lives have occurred. Well, what fraction of polonium remains? We want to half this 2.637 times, which gives me 0.161. This tells me whatever's over on the left-hand side, which is the amount that I have at time t, so the amount at 365 days, divided by that initial concentration. So this is the fraction remaining. What if I wanted to calculate percent? Well, we know how to turn fractions or decimal numbers into percent. If I multiplied this by 100, that would give me 16%. So 16% remains, which means 84% has reacted. Once we figure out this fraction, we can do percent, we can do what remains, we can do what's being used up. We just need to pay attention to whatever is being asked so that we can answer it appropriately. So once we know what happens according to first-order kinetics, we can use the integrated rate law. If it happens according to first-order kinetics, there's a really important concept of half-life that applies to lots of important situations, such as isotopic decay. And then we can use these nice little short-form equations. It's kind of fun. You could solve the integrated rate law order twice and still get here. So if you have another way of solving this type of problem, there's more than one right way to get to the correct answer. We have time for one more problem. The first order decomposition of N2O5 into nitrogen dioxide and oxygen has a half-life of 120 seconds. If the initial concentration for this reaction is as given, 0.85 moles per liter, what's its concentration going to be after 5 minutes have passed? Well, we could use the integrated first order rate law. That would be perfectly fine. We could also simply solve for the number of half-lives that have elapsed and solve it that way. I'm going to do it, I think this is a little bit simpler, so I'm going to do it this way. The time that elapsed is 5 minutes, and I know the length of a half-life is 120 seconds. If I stopped here and did 5 divided by 120, I'd get a small decimal number, which doesn't make sense because we know multiple half-lives have evolved. So I need to make sure that I include 1 minute is equal to 60 seconds, which gets me to 300 seconds divided by 120 seconds, gives me 2.5 half-lives have occurred. So what's the concentration after 2.5 half-lives have happened? Well, I know the starting concentration. I want to figure out the concentration at 5 minutes. I've now solved for the number of half-lives that have occurred. I can simply solve for the concentration of A at time t. And of course, A is the concentration of N2O5 for this problem. Therefore, the concentration of this reactant started at 0.85, and it's gone down, according to first-order kinetics, to 0.15 moles per liter. We can do this because we know it occurs according to first-order kinetics. But not every reaction is first-order kinetics. Sometimes it's zero order, sometimes it's second order, sometimes it's something else. When we come back on Friday, we'll see the zero and the second integrated rate laws. Have a fabulous day.